point charge. Intensity of intensity of electric field due to due to point charge. Point charge. Point charge. Intensity of electric field due to point charge. This is very, very important. It is very, very important. Now, this is a source charge. Capital Q is a source charge. Source charge. Source charge. Source charge. This is a point. This is a point. P point. Q naught is a. This is a Q naught. Q naught is a test charge. Q naught is a intensity of electric field. Electric field due to point charge. Point charge. Point charge. Intensity of electric field due to point charge. Point charge. This is a source charge. This is a source charge. Source charge. This is a point. This is a point. This is a P point. This is a Q naught. Q naught is a test charge. Q naught is a test charge. Test charge. Distance between the two charges is I'm taking R. I'm taking R. At this point, we have to calculate the intensity of electric field. At this point, we have to calculate the intensity of electric field at this point. Now, Coulomb's law applies between two charges. Coulomb's law applies between the two charges. Do you know Coulomb's law? F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is a Coulomb's inverse square law. This law applies. Next, F is equal to force between the two charges is equal to 1 by 4 pi epsilon naught. Q1 means capital Q. Q2 means this is a Q naught. Distance between two charges is R. I'm going to write R square. That is a R square. That is a force between the two charges. But we have to find out the intensity of electric field at P point. Now, do you know intensity of electric field? We know relation between intensity of electric field and force E is equal to F by Q. F by Q naught. This is a relation between intensity of electric field and the force. Now, I want E. I know F. So that is F is equal to, what's the F value? F is equal to 1 by 4 pi epsilon naught capital Q and small q by R square. Now, Q naught cancel each other. E is equal to intensity of electric field at P point is equal to EP. P means electric field at this point. Now, 1 by 4 pi epsilon naught capital Q by R square. This is intensity of electric field at P point. This is intensity of electric field at P point is equal to 1 by 4 pi epsilon naught Q by R square. This is intensity of electric field due to point charge. This is a very, very important in IP. Okay. Suppose, for example, this is a point Q charge. This is a P point. This is a Q naught. This is a vacuum between the two charges. Distance from here to here is R. Electric field is equal to vacuum is equal to 1 by 4 pi epsilon naught capital Q by R square. Capital by 1 by 4 pi epsilon naught Q by R square. Now, suppose this charge Q is, this is a distance between two charges is R, this is a P, this is medium between the two charges. Medium between the two charges. We have to find out intensity of electric field at the P point is equal to E medium is equal to 1 by 4 pi epsilon naught. Medium means K, dielectric constant, Q by R square. Q by R square. Q by R square. This is equation number 1. This is equation number 2. And divide the equation number 1 and equation number 2. EV by EM is equal to 1 by 4 pi epsilon naught capital Q by R squared by 1 by 4 pi epsilon naught capital Q by R squared. Now, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught cancel each other. This is 1 by K. So R cancel each other. This is 1 by 2. So EV by EM is equal to, now I'm going to write this is a 1 by 1, 1 by K. Now, you can write EV by EM is equal to, now this is a K. That is a relation. That is a relation. Intensity of electric field due to point charge. This is a capital Q. This is a point P. This is a test charge. Test charge kept at this point. So we have to calculate intensity of electric field at this point. That is intensity of electric field at this point is equal to 1 by 4 pi epsilon naught Q by R square. Now Q is at a test charge. This is a Coulomb's inverse square law. Coulomb inverse square law applies between two charges. Applies between the two charges. What will happen? What will happen? 1 by 4 pi epsilon. This is a medium between the two charges. Q1 means capital Q. Q2 means Q naught. Distance between the two charges is R. This is R square. So I want to, we know relation between intensity of electric field and force is E is equal to F by Q naught. E is equal to, F means 1 by 4 pi epsilon naught capital Q small q by R squared by Q naught. Now Q naught cancel each other. EP is equal to 1 by 4 pi epsilon naught Q by R squared. Suppose this is a vacuum. Intensity of electric field at this P point is equal to 1 by 4 pi epsilon naught Q by R squared. So this is a medium between the two charges. Intensity of electric field at this P point is equal to 1 by 4 pi epsilon naught 1 by K Q by R squared. Now 1 and 2. Divide the equation number 1, equation number 2. We are getting EV by EM is equal to K. K means dielectric constant. Dielectric constant or relative permittivity. Relative permittivity. Relative permittivity. Next, applications. Suppose, for example, This is a capital Q. This is a point charge. Q naught is a test charge. Test charge. Distance between 2 points is R. This is a distance between the two charges. Here I am placing, this is a dielectric constant. Dielectric constant. Dielectric constant. This is a dielectric constant. Dielectric constant. This is a T and dielectric constant K. Now, at this point, P point, we have to calculate intensity of electric field at this point. Now, electric field intensity, we have to find out intensity of electric field at P point is equal to, we know formula 1 by 4 pi epsilon naught capital Q by R square. This is a formula, I know. But here in vacuum means R minus T, R minus T. In another one, vacuum means vacuum is equal to T into root K, T into root K. Do you know this? Already I explained this one. So finally, total vacuum is equal to R minus T plus T root K. T root K. This is a total vacuum. Total vacuum. This is a total vacuum. Now, so what will happen in this situation? Now we'll see. So EP is equal to 1 by 4 pi epsilon naught capital Q by R means this is a distance between two charges is R minus T plus T root K whole square. This is a form. That is a form. Now you can take D means here. D means you can take D means what will happen? This is a D minus T. This is a D minus T. D minus T. That is a form. This is a very important. Very important. So we know this one. How can we calculate this one? Means you see this. So here I'm going to explain. This is a capital Q. This is a point P. Q naught is a test charge. Q naught is a place at this point. Distance between the two charges is D. Distance between the two charges is D. Now vacuum. Vacuum means this is a medium. Remaining part is vacuum. Remaining part. This is a remaining part is only. This is a medium. This is small part, and the thickness of this one is T. Distance between the two charges is D. Distance between the two charges is D. Remaining part, I want vacuum. Vacuum means D minus T means vacuum. And this part I am getting vacuum. అంటే ఈ టోటల్ డిస్టెన్స్ D లో నుంచి ఈ స్మాల్ పార్ట్ T ని తీసేస్తే ఇక్కడ మిగిలిన పార్ట్ లో మనకు వాక్యూమ్ వస్తుంది. దిస్ ఇస్ రిమైనింగ్ వాక్యూమ్. మిగిలిన పార్ట్ లో వాక్యూమ్ వస్తుంది. ఈ పార్ట్ లో వాక్యూమ్ కావాలంటే బినో what is this one? Do you know? Already I told you. So that is kr square. Kr square is called constant. Kr square is called constant. K1 R1 square is equal to K2 R2 square. R2 square. This is a vacuum. This is a medium. Vacuum means K is equal to K1 is equal to 1. K2 is equal to medium means K. Okay. Now K1 means 1. R1 square means R1 square. R1 square means here D square. D square is equal to K2 means K. R2 square means thickness T square. T square. This is D square. Take this side, root of KT square. KT square. D is equal to, this is root AB, root of A into root of B. I'm going to write. Now root K into T. Now this is D. D is equal to T into root of K. Root of K. Root of K. Now we will see total vacuum. This is a vacuum. This is a vacuum. Total vacuum. So I want a total vacuum. D minus T means this part vacuum, remaining part vacuum. But this part vacuum means T into root K, T into root K. Total vacuum means D minus T plus T root K. Okay, this value is okay. R means R is equal to R means D minus T plus 2 T root of K. That is your answer. Okay, keep in your mind, that is very important, very important. Now we will see the next one. This is a capital Q. This is a point P. At this Q naught is test charge. Test charge. This is a from here to here is a distance is D. Half of the part is filled with thickness T1 and K1. K1 is a dielectric constant. Thickness is T1. Remaining of a part is filled with the dielectric constant K2. Thickness is T2. But at this point, so what we have to calculate intensity of electric field at this point. Intensity of electric field at this point is equal to 1 by 4 pi epsilon naught capital Q by D square. Capital Q by D square. D means EP is equal to 1 by 4 pi epsilon naught capital Q by D means you can apply this formula. You can apply this formula here. First part is T1 root K1 plus second part T2 root K2 whole square. This is your answer. That is your answer. This is a very important points. Keep in mind. Okay. Next one. So next to electric field lines. Electric field lines. Electric field lines. Next concept is electric field lines. Electric field lines. Electric field lines. Now you will see electric field lines was introduced by Faraday. Electric field lines. The concept of electric field lines was introduced by the Faraday. Electric field lines. The concept of electric field lines was introduced by the Faraday. So electric field lines are imaginary lines. Imaginary lines. Now you will see the properties of electric field lines. Properties of electric field lines. Properties of electric field lines. First property. Now electric field line. For isolated charge. For isolated charge. Field lines are straight lines. For isolated charge, field lines are straight. Next, For a system, for a system of two or more charges, field lines are field lines are curved. Field lines are curve shape. Curve shape. Curve shape. You will see for isolated charts. For isolated charts, right? For a system of two or more charges, field lines are curve shape. Curve shape. Curve shape. Okay. For example, first example, curve shape. Curve shape. Next, third point. For example, first example. Example 1. This is a charge, positive charge, radially outward direction, straight direction, straight. Example 2. This is example number 1 and 2. This is a positive charge. This is a negative charge. Field lines start from positive to negative, terminate at a negative terminal. It starts like this. This is a line. This is a shape is. The shape is curve shape. This is a straight line. Straight line curve shape. That is example 1. Example. Next, third point is tangent drawn at any point on field line tangent drawn at any point on the field line gives direction of electric field line. Gives direction of field line. Direction of electric field. At that point. Tangent drawn at any point on the field line gives direction of electric field at that point. Now we will see this is a curve shape at this A point. This is electric field at this B point. This is a B point, electric field at this point. Tangent drawn at this is a tangent drawn. This is a tangent drawn at this point. This is one point. This is another point. Another point on the field line. This is a field line. Gives direction of electric field. At this point, direction of electric field at this time. At this point, direction of electric field is this direction. That's the point. Next, fourth point. So very, very important. No two fields two electric fields cannot intersect. No two electric field field lines. Field, two electric field lines, cannot intersect each other, cannot intersect each other. No two electric field lines cannot intersect each other. Intersect each other. For example, at this point, electric field at this one. Now electric field at this point. Field line number one, field line number two. Field line number one, field line number cause reason to field as electric field as 2 or more, 2 or 3 field as 2 or 3 field as, this is a field lines as 2 or 3 1 or 2 field line as 2 or 3 field as 2 or 3 direction of field, direction of field as 2 field as 2 or 3 direction of, okay, no, I will write direction of field, direction of field as 2, direction of field as 2. At same point, direction of field as 2. At the same point, which is not possible. It's not. Direction of field as 2 or more. Direction of field as 2 at the same point, which is not possible. Just not possible. Field as okay, now you will write direction of field as 2 or more at direction, field as 2 or more at direction, field as 2 or more direction at the same point, which is not possible. Field as 2 or more direction at the same point, which is not possible. Not possible. For isolated, fifth point, for positive for a positive isolated charge. For positive isolated charge. Charge. Field lines are radially outward direction, outward direction, outward direction, outward direction, outward direction. This is a positive charge. For example, this is a positive charge, isolated charge. Electric field is outward, radially outward direction. Radially, field lines are radially outward direction for positive charge. For negative charge, for negative charge, isolated charge, isolated charge, isolated charge. This is a negative charge. Negative charge. Electric field lines are inwards. 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 Field lines are inwards. Now, field lines are radially inward direction. Inward direction. Next, sixth point, inward direction. Number of field lines. Number of field lines. Number of field lines. Number of field lines. Divergent or convergent. Convergent. This is a lines. Lines are convergent. These lines are divergent. Divergent. Number of field lines convergent or divergent is directly proportional to charge. Directly proportional to charge. Directly proportional to charge. So electric field lines. Field has two or more directions at the same point, which is not positive. For positive charge, field lines are radially outwards. Radially outwards. Field lines are divergent. For negative charge, isolated charge, this is negative. Field lines are convergent. Field lines are radially inwards direction. Next, sixth point. Number of field lines are divergent or convergent directly proportional to the charge. Magnitude of charge. This is a magnitude of charge. Magnitude of charge. Magnitude of charge. Seventh point. So electric field lines, this is a positive charge, this is a negative charge. Electric field lines start from positive charge and terminating at negative point. Starting from positive, terminating at here. Starting here, terminating. Field lines, electric field lines are field lines are field lines are starting field lines are starting from positive charge and ending at negative charge. Field lines are starting from positive charge, ending at negative charge. Electric field lines are open loop, open loop, open loop, open loop, open loop. Next, 9 point. Number of lines number of lines linked with charge Q. Number of lines linked with the charge Q is equal to 1 by epsilon. 1 by epsilon. So next, number of field lines linked with the unit coulomb, 1 unit coulomb is equal to Q by epsilon naught, is called as flux. It's called as flux. It's called as flux. So next, 11th point. NLF by area directly proportional to the E. That means number of field lines of force for unit area normal to strength of electric field, strength of electric field. Number of field lines of force for unit area normal to the strength of electric field. 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 Field lines are starting from positive charge to negative charge, ending at negative charge. Field lines are open loop. Open. Number of field lines are linked with the Q is equal to 1 by epsilon. Number of field lines are linked with the 1C is equal to Q by epsilon, is called as flux. Number of field lines of force for unit area normal to the strength of electric field. Strength of electric field. Strength of electric field. Next, 12th point. This is a positive charge. This is a negative charge. So positive charge means electric field is outward direction. Negative charge means electric field is inwards. This is a symbol indicates electric field. Positive charge means direction of electric field is outward. Direction of electric field lines, and this is a surface of the conductor is 90 degrees. Angle between here is 90 degrees. This is a surface of the conductor. Field lines are field lines are normal to the surface of the of conductor. This is a very important. Field lines are, this is a field line, this is a field line, this is a surface of the conductor, This is surface of the conductor, this is a field line. Angle between here is 90 degrees. Field lines are normal to the surface of the conductor, This is example. For positive charges, this is example. For negative charges, for this example. Next, 13. No field lines. No field lines. Lines are present in a conductor. So no charge. No charge is present in a conductor. No field lines are present in a conductor. No charge is present in a conductor. Next, 14 point. Suppose this is a field lines. A point, this is a B point. A point and a B point. So electric field lines are or crowd that represent field lines are crowd. This is a field lines are crowd. 1, 2, 3, 4 are crowd. Field lines are crowd that represent field. Electric field is represented. Field lines are crowd that represent electric field. Field is maximum. Electric lines are crowd that represented electric field is maximum. At this point, suppose the field line are wider. Suppose you don't want this one. If wider, that represented the field, the electric field is a minimum. See here, strength of electric field is electric field is max. Here, this is a field lines are wider. Here, crowd. Field lines are crowd. Electric field is maximum. Field lines are wider. If wider field lines, here electric field is minimum. Field lines are minimum. It's a minimum. Now, next point, last point. Field lines are imaginary lines. Field lines are imaginary. Imaginary. Field lines are imaginary. Do not have physical significance. Physical significance. Significance. Physical significance. Field lines are imaginary. Field lines are imaginary. Do not have physical significance. Physical significance. This is a properties of electric field lines. Electric field lines. Properties of electric field lines. Field lines are normal to the surface of the conductor. This is a surface of the conductor. This is a field line. Angle between field line, surface of the conductor. Angle between surface of the conductor and normal is field line. This is a field line. This is surface of the conductor. Angle between two is 90 degrees. That is a 90 means normal. Normal means perpendicular. No field lines are present in a conductor. No charge is present in a conductor. So this is electric field. This is 1, 2, 3, 4. All lines are very near. Crowd. Field lines are crowd. Electric field is maximum. Field lines are wider. This distance between the two lines is more. So electric field is minimum. If wider lines, this is a field lines are wider. Electric field is minimum. Minimum electric field lines. So last point. So electric field lines are electric field lines are parallel. Electric field lines are parallel, equally spaced. Electric equally spaced. Now, for example, this is a one electric field line. This is another electric field. This is a one more electric field. This is another electric field. This is a one line, second line, third line, fourth line. All electric field lines are parallelly equidistant. I mean, electric field lines are parallel and equally spaced. The represent is called as uniform electric field. Uniform electric field. Electric field lines are parallel and equally spaced. The represent and uniform electric field. Uniform electric field. Uniform electric field. Uniform electric. Electric field lines are parallel and equally spaced. Stay on. So wait in the online.
Good morning, everybody.